Chapter 13, Magnetic Effects of Electric Current. In the previous chapter on electricity, we learnt about the heating effects of electric current. What could be the other effects of electric current? In this chapter, we are going to cover following points. Introduction to the topic. Introduction to magnetism. Magnetic field and field lines. Magnetic field due to a current carrying conductor. Magnetic field due to a current through a straight conductor. Right-hand thumb rule. Magnetic field due to a current through a circular loop. Magnetic field due to a current in a solenoid. Force on a current carrying conductor in a magnetic field. Electric motor. Electromagnetic induction. Electric generator. Domestic electric circuits. Introduction to the topic. Take a straight thick copper wire and place it between the points X and Y in an electric circuit. Place a small compass near to this copper wire. See the position of its needle. Pass the current through the circuit by inserting the key into the plug. Observe the change in the position of the compass needle.
Introduction to magnetism. Magnets are solid objects of stone, metal, or other material which have the property of attracting iron-containing materials. This attracting property is either natural, as in the case of lodestone, or induced, formed by unnatural means. The term magnetism comes from Magnesia, the naming of a region within Asia Minor exactly where lodestone, the naturally magnetic iron ore, was discovered in ancient times. Magnetism is the force where objects are attracted or repelled to one another without physically touching. Usually these objects are metals such as iron. Iron, cobalt, nickel are some materials which are easily magnetized whenever put into a magnetic field. Magnets may also be formed that are known as electromagnets. A basic electromagnet is created using a battery as well as copper wire coiled close to a metal rod like a nail. Magnetic field. The region around a magnet where the force of attraction or repulsion can be detected is called magnetic field. Magnetic field around a magnet can be detected by using a magnetic compass. Magnetic field lines. Magnetic field lines are the paths around a magnet along which the north pole of a magnetic compass needle tends to move. The imaginary lines of magnetic field around a magnet are called field line or field line of magnet. When iron fillings are allowed to settle around a bar magnet, the magnet exerts its influence in the region surrounding it. Therefore, the iron fillings experience a force. The force thus exerted makes iron fillings to arrange in a pattern. The region surrounding a magnet in which the force of the magnet can be detected is said to have a magnetic field. The lines along which the iron fillings align themselves represent magnetic field lines. It can also be observed by moving a magnetic compass around a magnet. Direction of field line. Outside the magnet, the direction of magnetic field line is taken from North Pole to South Pole. Inside the magnet, the direction of magnetic field line is taken from South Pole to North Pole. Strength of magnetic field. The relative strength of the magnetic field is shown by the degree of closeness of the field lines. The field is stronger, that is, the force acting on the pole of another magnet placed is greater where the field lines are crowded. Magnetic field and field lines. Properties of magnetic field. Lines of force are closed and continuous curves which are due to the fact that isolated magnetic poles do not exist. The direction of magnetic field lines outside the magnet is from North Pole to South Pole. The direction of magnetic field lines inside the magnet is from South Pole to the North Pole. Lines of force repel each other. Lines of force never intersect. magnetic field lines are always parallel to each other. In the regions of stronger magnetic field, the magnetic field lines are crowded, and in the regions of weaker magnetic field, they are far apart. Crowded field lines are seen near the poles of magnet, indicating stronger magnetic field. Magnetic field due to a current-carrying conductor. The connection between electric current and magnetic field was first observed when the presence of a current in a wire near a magnetic compass affected the direction of the compass needle. We now know that current gives rise to magnetic fields, just as electric charge gives rise to electric fields. An electromagnet can be produced by conducting a current through a conductor. If the current flows from north to south in a metallic conductor, the north pole of the compass needle would move towards the east. If we change the direction of current through the copper wire, that is from south to north, there will be a change in the direction of deflection of needle. The needle moves in the opposite direction, that is, towards the west. Magnetic field around a straight conductor. The strength of the magnetic field created depends on the current through the conductor. A current-carrying straight conductor has magnetic field in the form of concentric circles around it. Magnetic field of current-carrying straight conductor can be shown by magnetic field lines. The direction of magnetic field through a current-carrying conductor depends upon the direction of flow of electric current. The direction of magnetic field gets reversed in case of a change in the direction of electric current. Properties of magnetic lines of forces around the straight conductor. Number 1. The magnetic lines of forces are in the form of concentric circles near the conductor. Number 2. On changing the direction of the current, the direction of the magnitude lines also reverses. Number 3. On increasing the magnitude of the current, the magnetic lines of forces increase. Number 4. The plane of magnetic lines of force is at right angle to the plane of the current-carrying conductor. Right-hand thumb rule. The direction of magnetic field in relation to direction of electric current through a straight conductor can be depicted by using the right-hand thumb rule. It is also known as Maxwell's corkscrew rule. The right-hand thumb rule. If the right hand is imagined to have held the conductor that carries the current in a manner where the pointing of the thumb is along the direction of the current, then the magnetic field lines are determined with the help of direction that the wrapped fingers point. This formulates that if the current in the wire flows vertically in the upward direction, the lines in the magnetic field move in the anti-clockwise direction. Similarly, if the current in the wire flows vertically downwards, the lines in the magnetic field move in clockwise direction.
Magnetic field due to a current through a circular loop. We have so far observed the pattern of the magnetic field lines produced around a current-carrying straight wire. Suppose this straight wire is bent in the form of a circular loop and a current is passed through it. How would the magnetic field lines look like? We know that the magnetic field produced by a current-carrying straight wire depends inversely on the distance from it. Similarly, at every point of a current-carrying circular loop, the concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire. By the time we reach at the center of the circular loop, the arcs of these big circles would appear as straight lines. Every point on the wire carrying current would give rise to the magnetic field appearing as straight lines at the center of the loop. By applying the right-hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop. This rule is also called Maxwell's corkscrew rule.
Magnetic field due to current in a solenoid. A coil of many turns of insulated copper wire wrapped in the shape of cylinder is called a solenoid. The magnetic field lines in a solenoid through which current is passed are shown in figure. These lines are similar to that of the lines of a bar magnet as shown in figure. One end of the coil acts as south pole and the other end as north pole. Thus, solenoid has all the properties of the field produced by a bar magnet. With the help of a solenoid, we can magnetize a piece of rod of a given material. If the rod is hard steel and if the magnetic field is strong enough, a permanent magnet can be produced. Permanent magnets are usually made of carbon steel, chromium steel, cobalt, and tungsten steel and some alloys. Two such alloys which are used in industry are Nippermag and Alnico. Nippermag is an alloy of iron, nickel, aluminium, and titanium. Alnico is aluminium-nickel-cobalt alloy. Permanent magnets of such alloys are used in microphones, loudspeakers, electric clocks, and many other devices like ammeters, voltmeters, and speedometers, etc.
Force on a current-carrying conductor in a magnetic field. We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on a magnet placed in the vicinity of the conductor. French scientist Henri-Marie Ampère (1775–1836) suggested that the magnet must also exert an equal and opposite force on the current-carrying conductor. The force due to a magnetic field acting on a current-carrying conductor can be demonstrated through the following activity. Take a small aluminium rod AB of about 5 cm. Using two connecting wires, suspend it horizontally from a stand. Place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. For this, put the north pole of the magnet vertically below and south pole vertically above the aluminium rod. Connect the aluminium rod in series with a battery, a key and a rheostat. Now pass a current through the aluminium rod from end B to end A. What do you observe? It is observed that the rod is displaced towards the left. You will notice that the rod gets displaced. Reverse the direction of current flowing through the rod and observe the direction of its displacement. It is now towards the right. Why does the rod get displaced? The displacement of the rod in the above activity suggests that a force is exerted on the current-carrying aluminium rod when it is placed in a magnetic field. It also suggests that the direction of force is also reversed when the direction of current through the conductor is reversed. Now change the direction of field to vertically downwards by interchanging the two poles of the magnet. It is once again observed that the direction of force acting on the current-carrying rod gets reversed. It shows that the direction of the force on the conductor depends upon the direction of current and the direction of the magnetic field. Experiments have shown that the displacement of the rod is largest or the magnitude of the force is the highest when the direction of current is at right angles to the direction of the magnetic field. In such a condition, we can use a simple rule to find the direction of the force on the conductor. In this activity, we considered the direction of the current and that of the magnetic field perpendicular to each other and found that the force is perpendicular to both of them. The three directions can be illustrated through a simple rule called Fleming's left-hand rule. According to this rule, stretch the thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular. If the first finger points in the direction of magnetic field and the second finger in the direction of current, then the thumb will point in the direction of motion or the force acting on the conductor. Devices that use current-carrying conductors and magnetic fields include electric motor, electric generator, loudspeakers, microphones and measuring instruments. In the next few sections we shall study about electric motors and generators. Let's study one question regarding this. An electron enters a magnetic field at right angles to it. What will be the direction of force acting on the electron? A. To the right, B. To the left, C. Out of the page, D. Into the page.
Electric motor. A device which converts electrical energy into mechanical energy is called an electric motor. Principle. Electric motor works on the principle that a current-carrying conductor placed in a magnetic field experiences a force. The components of electric motor are: Number 1. Armature coil. A large number of turns of insulated copper wire wound on iron core in rectangular shape forms an armature coil ABCD as shown in the figure. Number 2. Strong magnet. The armature coil is placed in between two pole pieces, north and south, of a strong magnet. This provides a strong magnetic field. Number 3. Split ring commutator. It consists of two halves, R1 and R2 of a metallic ring. The ends of the armature coil are connected to these rings. Commutator reverses the direction of current in the armature coil. Number 4. Brushes. Two carbon brushes B1 and B2 are used to press the commutator. Number 5. Battery. The battery supplies the current to the armature coil. Working of the electric motor. When current is passed through the coil ABCD, arms AB and CD experience force. According to Fleming's left-hand rule, the force experienced by arm AB is in the upward direction and arm CD in the downward direction. Both these forces are equal and opposite. This force rotates the coil in clockwise direction until the coil is vertical. At this position, the contact between commutator and brushes breaks, so the supply to the coil is cut off. Thus, no force acts on the coil. But the coil does not stop due to inertia. It goes on rotating until the commutator again comes in contact with the brushes B1 and B2. Again, the current starts passing through the coil and the arm AB rotates through 90 degree, 180 degree, 270 degree, and 360 degrees. Now the force acting on arm AB is downward and arm CD is upward. Again, this force moves the coil in clockwise direction. Thus, the coil rotates with the help of electrical energy. The coil of DC motor continues to rotate in the same direction.
According to this principle, whenever magnetic field around a conductor changes, a potential difference is generated across the conductor. Let us understand this. Take a circular coil and connect two ends of this coil to galvanometer to measure potential difference. This circuit has no source of electricity and the galvanometer initially shows 0 reading. The field around a coil can be changed in two ways. Case number 1. If a conductor is stationary and magnet is rotating, the field around the conductor changes. Now take a bar magnet and move it across the coil facing north pole towards the coil. You will observe that there is a deflection in the galvanometer, indicating current is generated in the coil. Now if you move magnet away from the coil, you will again get deflection, but in opposite direction. Case number 2. If a magnet is stationary, but the conductor is moving, then also the field around the conductor will change. Now if you keep the bar magnet at rest and move the coil, the galvanometer again shows deflection. Thus, in both cases, a potential difference is created across the conductor.
AC generator. Construction. The main components of AC generator. Number 1. Armature. Number 2. Strong magnets. Number 3. Slip rings and Number 4. Brushes. Armature, strong magnet and brushes are the same as used for electric motors. Slip rings. The two ends of the armature coil are connected to two brass slit rings R1 and R2. These rings rotate along with the armature coil. Working. When the armature coil ABCD rotates in the magnetic field provided by the strong magnets, it cuts the magnetic lines of forces. Thus, the changing magnetic field produces induced current in the coil. The direction of induced current is determined by the Fleming's right-hand rule. The current flows out through the brush B1 in one direction in the first half of the revolution and through the brush B2 in the next half revolution. In the reverse direction, this process is repeated. Therefore, the induced current produced is of alternating nature. Such a current is called as alternating current.
Domestic electric circuits. In our homes, we receive supply of electric power through a main supply, also called mains, either supported through overhead electric poles or by underground cables. One of the wires in this supply, usually with red insulation cover, is called live wire or positive. Another wire, with black insulation, is called neutral wire or negative. In our country, the potential difference between the two is 220 volt. At the meter board in the house, these wires pass into an electricity meter through a main fuse. Through the main switch they are connected to the line wires in the house. These wires supply electricity to separate circuits within the house. Often, two separate circuits are used. One of 15 ampere current rating for appliances with higher power ratings such as geysers, air coolers, etc. The other circuit is of 5 ampere current rating for bulbs, fans, etc. The earth wire, which has insulation of green color, is usually connected to a metal plate deep in the earth near the house. This is used as a safety measure, especially for those appliances that have a metallic body, for example, electric press, toaster, table fan, refrigerator, etc. The metallic body is connected to the earth wire, which provides a low resistance conducting path for the current. In each separate circuit, different appliances can be connected across the live and neutral wires. Each appliance has a separate switch to on/off the flow of current through it. In order that each appliance has equal potential difference, they are connected parallel to each other. Electric fuse is an important component of all domestic circuits. We have already studied the principle and working of a fuse in the previous chapter. A fuse in a circuit prevents damage to the appliances and the circuit due to overloading. Overloading can occur when the live wire and the neutral wire come into direct contact. In such a situation, the current in the circuit abruptly increases. This is called short-circuiting. The use of an electric fuse prevents the electric circuit and the appliance from a possible damage by stopping the flow of unduly high electric current. The joule heating that takes place in the fuse melts it to break the electric circuit. Overloading can also occur due to an accidental hike in the supply voltage. Sometimes overloading is caused by connecting too many appliances to a single socket.